Greetings to the Tom Wood School of Life. I am kicking off a series of webinars that talk about how I do business analysis. I was sitting around thinking about how to write this up and developing my first set of slides. And I said, Bob, I always call myself Bob. I said, Bob, this is kind of dry. So why don't we actually talk about what inspired my way of thinking about this? And that was based on having done computer simulation of various kinds throughout almost all of my career, which now spans close to 35 years after I got out of the Army and college. So, for those of you who don't know me, my nervous system has decided it would rather be in Pago Pago than anywhere near me. So, the speech is not optimal, but I press ahead anyway. If you would prefer, you can watch the recordings that will be posted on my website, and you can watch them speeded up by 1.5, 1 3/4, even double speed, and I start to sound something closer to normal. One thing I'll tell you about these slides, they are rendered in the reveal.js framework, so they're hosted natively on my website, which is at rpchurchill.com. And every time you see a link like here, you can go to slides, blog posts, Wikipedia articles, videos, and other materials and files that I've linked as supporting information. There's quite a lot of that. Now, out of the way, we will begin. So, I've worked in a lot of different industries, and I've done simulations, written them, developed them, employed them for various reasons. Here are all the industries and some of the applications I've worked on. I'm sure you can think of many others. By the way, I also want to tell you that I've given presentations and series in the past, and the goal of this series is to do more of them and shorter. So the idea is to make them all be about a half an hour, make them short and sweet, get in, get out, cover a lot of things, and not take up too much of anyone's time at once. So why do we build and run simulations? The first reason we do it is for situations which are too dangerous or expensive or whatever to do in the real world. For example, if you want to have a nuclear power plant training simulator, you want people to be able to respond to really bad goings on when things go wrong, but you don't actually want to have those things happen in real life. I ended up working on power plant simulators because 3 Mile Island happened. And they realized when they did a post-mortem that the operators had lost situational awareness. And if they just walked away, the plant would have shut down safely. So a lot can be learned. Another reason is to calculate values that cannot be measured directly. I'll give you an example of that in a minute. There are many times when it is impossible to do experiments. You can also check out a lot of options and you can understand a range of possible outcomes under combinations of various events. So there are a lot of reasons to do these. There are major classes of simulations. I'll actually jump down into the middle. So the first one I'll talk about is continuous simulations. They're based on physics, which are described by differential equations. Fluid mechanics, heat transfer, electrical circuits, and mechanical systems that involve springs, masses, shock absorbers, and so on. Now, you can do analog simulations of all those systems using mechanical systems or electrical circuits that stand in for all the analogous parts of other types of systems. There are whole classes of problems that can be solved this way. The other major class of simulation is discrete event. And that means you process events whenever they happen and look at the logical outcomes of each event. And you run ideally multiple trials and you get a statistical outcome. That's one way of doing it. So obviously you can have hybrid combinations of all those. The initial simulators were really small and really simple for training simulators. When they were practicing bombing runs of Tokyo, they actually rigged up little compartments that would fly over a giant paper mache model of Tokyo and the harbor and the mountains and the areas beyond the city, and have the pilots fly over and the bombardiers look through sites to get them used to what they would be seeing, the timing and the lay of the land and so on, in a way that was more realistic than maps. So there are many kinds of simulations. This one is in Sausalito, and I always found it fascinating. It's a couple acres in size, and it was used to originally evaluate evaporation when they were thinking about walling off part of the bay. And they still use it for various things. There's a lot going on in that model, but again, it's another mechanical type simulation, or at least a physical one. So, like I said, there are electrical circuit analogs to many other kinds of physical situations and areas of study. Here's another way of describing all that in more detail. And obviously, we have hybrids, which are situations of all of these. A classic thing to do is build a continuous simulation that handles events that happen in the middle of time steps. One thing about continuous simulation, they are linearized differential equations typically executed on the same interval every time. So there are many different applications for simulation. I've worked on all these, others are certainly possible. Operations research allows you to figure out, if you do that, this thing, what will happen. It allows you to do things better, figure out costs, and so on. Real-time control is for control systems where there's something you can't measure directly. Design and sizing. We did building evacuation, security at border crossings and airports, operator training for nuclear power plants and other situations, economic analysis, and so on. There are a number of architectural considerations, and I will get into those in the future. Now, notice there are links to different blog posts I've written that go into detail on all these. So these are two animations of different kinds of simulations. The one on the left is a thermal simulation of the temperature in a cross-section of a steel billet being reheated in a furnace. And it's lying on the right side that's close to you, and the heat is coming in from the top and sides. So you see how the outside is heated from the heat the bar can see, and then also how the heat is conducted into the middle. When we roll these things out, we want the bar to be heated all the way through, and we cannot measure what's going on inside the bar, but we can model it. The item on the right is a discrete event simulation that is calculating what happens as items come into, wait in, or processed by and pass through different parts of a system. So I have a lot of blog posts that describe many facets of how continuous simulation works. Here's an example of a very simple fluid system with just a handful of nodes and connections. If I were going to write the equations out for them, they would be as appears in the leftmost panel here. And if you notice in the middle panel, I've colored them to show you that all the kinds of continuous simulation problems I've talked about are symmetric about that diagonal axis. So some clever people figured out how to simplify the problem down and solve the system of simultaneous equations using only half the matrix that is unique. So there are a lot of things you might need to know about dealing with continuous simulation. This is one method of one way of solving those. There are many. Here's a seemingly more complicated situation or equation that describes the heating of areas or elements within a steel bar. here's how each node works, and we simulate the total energy and temperature of each node and the heat transfer with the exterior environment and conducted within the nodes inside the piece. So with that 25 node model, we write the equations out and we simplify it and streamline it, then we can solve it. One of the many interesting ways to do this process faster, when you do this in code matrix solution routine or bit of code will actually have multiple loops inside loops. And calculating the memory offsets inside those loops actually takes a lot of time, more than you would think. So if you write all the codes out, all the lines out, with all the offsets pre-calculated in a process called extreme loop unrolling, you can actually make the whole thing run about 30% faster. So there are many different types of systems I have simulated. One example is the off-gas system in a power plant. Many of these systems I modeled at that job were simpler. This one was the most complex, and it turned out to be very difficult to do. Most people did not appreciate what was going on in this model. And it was actually 3 pages of this much stuff and not just that page. A discrete event simulation, like I said, deals with queues. They're often called queuing models, but they deal with many different things going on at the same time. So what you do is process events in time, and very often you will revisit what happens to a single item within the simulation as over and over again as it moves. For example, if cars driving down the road, you will update its position every 1 or 2 seconds. And I have some description here of what a queue looks like as different events happen in time. Normally, they're processed in time order. When things happen at exactly the same time, they can be processed either first come, first served, or in some other priority kind of way. And there are also wait until conditions that have to be processed differently. So I describe all this in a blog post there too. I will give you a little demo of what such a simulation looks like running live. This is on my website. It is written in JavaScript. It runs, so you can see it running in 2D and 3D. And when it finishes, it calculates a whole bunch of statistics for what happened in all the different sub areas of the system being modeled in the overall system. And there are a zillion ways to do this. This calculated all the numbers on the fly, but many times simulations will just record everything that happens and then do some kind of post-processing passes to figure all this stuff out. And there's also a link to the project. I actually wrote 92 different blog posts about how I developed this, what's happening. There's stuff about JavaScript and so on. So now we get into the architectural considerations. The first one is whether something is interactive or fire and forget. So interactive is like a video game. You do something and what the simulation or the game or the system does responds based on what you did. Fire and forget means you hit go and it does its thing and no further intervention is possible. When I was in the Army, I was in the air defense artillery, and there are two kinds of air defense missiles. An infrared missile will be locked onto a target, and when you fire it, the missile does all the tracking on its own. This particular system is called a command guided missile, and it tracks the aircraft and it tracks the missile and it sends continuous commands to the missile to get it to work. Oh, you can see the video if you want. The reason I included the rapier is because it's one of about 5 or 6 systems I trained on, and I actually got to go to England and drive this thing around and train on it, including the really cool helmet you use to acquire targets. Design and analysis simulations, you generally want to have them run as fast as possible. They don't do interaction. You can actually look at an API file I have stored if you want to see what's going on. That is up a border crossing. It is the busiest commercial border crossing in the US. It happened to be in Detroit. It's the Ambassador Bridge that crosses over to Windsor. So real-time versus non-real-time is another consideration. That movie is still capped from the China syndrome. That's Jack Lemmon and Wilford Brimley in the picture. So we build simulators that consisted of a duplicate of every panel, button, switch, dial, readout, light, and so on in the actual power plant. But instead of hooking it to the actual plant and running it, you hook it to a simulation, and it should be interactive and it should work at the same speed as the actual plant does. So that's real time. Another use of real time is responding to events as they occur. So model-based predictive control systems are called real-time systems. A non-real-time system is one that runs as fast as you can get it to run, and that may or may not include interaction. For example, if you're going to simulate the formation of the solar system, you don't want to wait around 4.3 billion years to get a result. You just want to run something fairly quickly and see what happens. Another consideration is single platform versus distributed. SimCity runs on one computer, a desktop, tablet, phone, etc. But more complicated systems like military simulations and dungeon crawls and things for video games might involve a whole bunch of computers networked together, and there are various protocols for making everything work together and stay in sync. Another consideration is deterministic versus stochastic. Deterministic ones, and they're generally physical. When you put in one set of inputs, you get the same outputs all the time. You only get one answer. Many events in life, however, different things happen all the time. Things happen in different orders, and a different number of people show up to be serviced. The rules are different on different days. And in those cases, you run a whole bunch of simulations and see what the range of outcomes is. And the distributions might be bell curve. They might be a curve with a long tail of much longer or occasionally very much shorter results. And the results should be described statistically and not as a point outcome. Monte Carlo analysis is really how you run multiple trials while including random elements. And this slide describes all the different parts of a simulation you can vary. And there are a lot of ways of building different functions for different outcomes. They come in all shapes and sizes. They can be random. They should be based on observed data. What a predictive control is, if we keep doing what we're doing, are we going to get the answer we want? And if we aren't, then let's change something. So I wrote simulations for control systems for these 800-foot steel furnaces. And those big sections here and here would swivel. So steel would come in from the caster, not shown toward you, run down to the end. The swivels would swivel, they transfer into the first line and go out to a single rolling machine. And the way this looks when they were actually running is like this. This particular two-line furnace used shuttles instead of swivels. And we built a number of them. And obviously, you can graph outputs, have controls for the simulation, track a lot of different values, and so on. So simulations can be as complex as you want. Process automation is an example of doing activities that used to be done by humans. Any business or other system can, in a way, be thought of as a person in the loop simulation. And there are ways to interact with systems and automate a human interacting with a user interface. and there are a lot of ways to do that. Resources required to do simulation or computing power, duty cycle, memory, input data, behavioral data, doing all on the right scope and scale, and generating outputs that serve some use that you can actually act on. There are a lot of ways to make simulations more accurate, better information, more granularity, and so on, making sure you calculate and correctly understand all possible effects. If we're going to simulate an atom, let's think about that. If we're going to do it in a computer, we have to talk about the atom's mass, its temperature, its location, its velocity, its atomic structure, the energy states of all its atoms, what happens when it absorbs energy and emits energy, and so on. And if we represented that as variables in a computer, that would take a huge amount of atoms to do. So obviously, we cannot write a computer simulation of the entire universe. The universe is actually analog simulation of itself. And I have a couple of references to simulations that occur in different kinds of science fiction. There are many things that govern the accuracy of simulation, including having reasonable data, and we need to keep in mind that all simulations are wrong, some are useful, and you need to understand the way simulations are wrong when you're doing them. Now, here I've written out a list of problems associated with some of the famous kinds of models you hear about all the time, because I've worked on all these kind of models and followed them for over 40 years in some cases. I've seen where a lot of the bodies are buried. And there are some common issues that generate errors in all types of simulations. So now we've reached the end. Thank you very much for attending and watching. My website is at rpchurchill.com. You can find links to my slides, recordings, and so on of different presentations on the portfolio page under presentations. Here you also have my email and LinkedIn. Those are both also on my resume page. And thank you very much. Please feel free to send me questions by email or make comments on any of the areas in Rocket Chat and so on. Thanks a bunch. See ya.